Okay, so this is the third of our structure and symmetry symposium lectures, divided into three like four. And this is going to be Ciprian Manolescu talking about annulation conjecture, that electrifying result we obtained 2 years ago. I should just say one thing. I should thank the London Mathematics Society for contributing to this talk today. Thank you very much. Ciprian.
Thank you for suggesting the LMS branch for me to come visit here. It's a pleasure to be in Edinburgh. So I will talk about triangulations of manifolds, and well, just to set the terminology straight, the triangulation is a homeomorphism from a space to a simplicial complex. And you can ask whether manifolds have such things, and there are actually three different questions one can ask. So the first question was, in a sense, asked by Poincaré in 1899. And in modern language, so Poincaré introduced two ways of constructing spaces, well, maybe three, in topology. One was by gluing polyhedra, and one was basically what now is known as smooth manifolds. So he asked, in modern language, his question would be, is any smooth manifold triangulable? And he actually tried to give a proof, but the proof was not rigorous. So the answer was later found to be yes. So this is the work of Cairns, I think building on the work of Whitehead from 1940. So in this case, every smooth manifold has a smooth triangulation, and this is unique in a sense. But there's a more interesting question, which was raised by Kneser in 1924. Is every topological manifold triangulable? So, for a while people believed that the answer was yes, and this was the triangulation conjecture, but, the answer is no. It depends on the dimension, so in small dimensions, less or equal than 3, the answer is yes. So, this was Rado in dimension 2, and Moise in dimension 3. And then, so the first counterexample was found in dimension 4. So there the answer is no. And this is, this basically follows, this is an application of the Casson invariant. So using the Casson invariant, one can show that Friedmann's E8 manifold is not triangulable. So this was then many other manifolds, 4 manifolds. So today I will talk about dimensions greater or equal than 5, where the answer is also no, and the proof has basically 2 distinct parts. So the first one was done by Gałowski, Stern, and Matsumoto in the 70s. And what they did is they reduced this. So this question to a question in 3+1 dimensions. So triangulability of high-dimensional manifolds is equivalent to some question, a different question about cobordisms between 3-dimensional manifolds. And then, so the solution of that problem is what I did 2 years ago. So the solution involves low-dimensional topology and, in fact, gauge theory. All right. So So now since we're here, let me also mention the third version of this, which in a sense is more natural, but was answered before. So is every, or does every topological manifold have a PL, piecewise linear structure? So this is the combinatorial triangulation question, because a piecewise linear structure is the same as having a triangulation where the links are spheres. So if we have a vertex in a simplicial complex, we can look at the link of that vertex, which is basically this. You look at all the simplices that contain V, and then take their closure, and then in there we look at the simplices that do not contain V. So this is the link. And similarly, you can look at some other simplex, and then there is something called the link of the simplex. And if these things are spheres, in fact, it suffices for this to be piecewise linearly a sphere. Then locally, this looks like cone on a sphere, which is Rn. So this is the kind of, and therefore this is a manifold. So this is the kind of triangulation where it is apparent from the triangulation that the space is a manifold. And whereas here we ask for also any possible triangulation. So this is a stronger question, and well, the answers are the same as before, but they were known before. So dimension 3 less or equal than 3 is yes. Dimension, so the first kind of negative answer was in dimension greater or equal than 5. So in 1969, this was the work of Kirby and Zieberman. So they showed that there exists an obstruction so for every manifold of dimension greater or equal than 5, you can define an element, delta of m, in the fourth cohomology with Zima2 coefficients, and the manifold is piecewise linear if and only if this obstruction vanishes. So this is the Kirby-Zieberman embedding. And then in dimension 4, this was the work of Friedman. So before Caston proved that, say, the E8 manifold is not triangulable, already from the work of Friedman, well, that's basically because in dimension 4, PL is the same as smooth. It followed that this manifold and others do not have piecewise linear structures. So in this dimension I should mention, you have delta, but you also have other obstructions coming from gauge theory, for example, Donaldson's diagonalizability theorem. Right, so somehow this was known before. So to understand the difference between these two, well, let me first. I mean, it's not even clear that what a non-PL triangulation of a manifold would be. So something where the links are not spheres, and this was an open question for a while, but such things exist. So non-PL triangulations of manifolds exist. This was the work of Bob Edwards and Jim Cannon from the 70s. And here's the typical example. So we start with a non-trivial homology sphere that's triangulated. So let's say Mn is a homology sphere that's not simply connected. So you could take the Poincare sphere in dimension 3. And then you do, well, you take the suspension of it as a simplicial complex. You put cones on both sides, and well, it turns out that well, here you have a loop that's not contractible, so you end up with a loop in a neighborhood of the point that is not contractible if you take out the point. And that's not the kind of thing that happens in a manifold. So what we can see is that sigma of n is not a manifold. Right. But what you can do next is take the double suspension. So take the suspension once more, and you look at sigma squared of m. And what Edwards and Cannon proved was that there exists a homeomorphism between this and the n plus 2-dimensional sphere. So, I mean, this is the hard part of the argument, but once you believe that this is a sphere, then if you look at this vertex v, then the link of v is this space. So the link of v is this is sigma of m. And sigma of m is not a manifold, in particular not a sphere. So this is not a piecewise linear structure, but it's some triangulation of a different kind on a manifold. All right, so the first part of my talk, I will try to explain well, the work of Galuski, Stern, and Matsumoto. So what does this question about triangulating high-dimensional manifold have to do with low dimensions? So this is part one. So yes, what I'm going to say is basically I learned from Andrew's survey online. So yes, I mean, there are people in the audience who know this better than me, but
well, I just compiled what other people did.
Yes. All right, so let's, okay, so to start, let me explain a little bit about this delta of m. So the curve is even one. So if you're interested in PL structures, you have this element, and this can be viewed as basically obstruction to lifting a map from, well, from where? From B top to BG. No, sorry, to BPL. So M is a topological manifold. It has some topological tangent space, and that's classified by a map to some classifying space. And then you want to lift it to some map to that would give it a piecewise linear at the level, a piecewise linear structure at the level of the tangent space, and then, well, you can actually turn that into an actual PL structure on the manifold. So there is such a definition for any M, but there is a more intuitive definition if M has a triangulation. So if M already has a triangulation, but it may not be piecewise linear. All right, and here let's say the dimension of M is greater or equal than 5, and let's say M is oriented for simplicity, but you can do it when it's not oriented as well. So then we define the following element, C of K is equal to a sum over codimensions for simplices in K. We take the link of sigma times sigma, and this will be a cocycle in, well, a cycle, I guess, in Hn minus 4 of M with values in some group, theta 3H, which, assuming orientability, becomes a cohomology group, theta 3H. So,
the link,
right.
link is here is a sphere.
It is not. So we have something of codimension 4, and the link, so if this was PL, then it would be a three-dimensional sphere. If it's not, you can show, using my review tourist, basically that this is a homology to the sphere. And yes, in fact, it has to be a manifold. Right, so, and what is theta 3H? Is the group of such homology 3 spheres, so oriented homology 3 spheres under an equivalence relation where two manifolds are equivalent. If there exists some, well, PL or equivalently smooth, since we're in dimension 4, cobordism between y0 and y1, right, such that they include, well, such that the relative homologies w, yi are 0. So this is homology cobordism. So this is a group. You can use connected sum to turn it into a group, and S3 is the 0 element. Right, and so basically out of these links you get an element in the cohomology of M with coefficients in that, and I should say why we're focusing on dimension 3. This is because theta, you can define this in any dimension, but it's 0 if n is different from 3.
And what is it if n equals 3?
We don't know. That's a good question. So we know some things about it. We know that it's infinitely generated. We know that it has a Z summand, and that's it. We don't know if it has any torsion. We don't know if it has infinitely many Z summands, if it has some Q or something. So yes, it's a complicated group.
Is the fact that it's 0 for all n other than 3 hard?
It uses some surgery theory. Basically, it's in the end it comes down to the fact that H cobordism works in high dimensions, and then in dimension 3 you have a problem. Okay, yes. So what, let me explain first how do you see that this group is non-trivial. There is the simplest way to see it is using the Rochlin homomorphism. So there is a surjective map from theta 3H to sigma 2, given by mu of y is signature of W over H mod 2, where W is a spin for manifold with boundary y. So if y is S3, then, well, you can just add a ball and make it a closed, and then you know by Rochlin's theorem that the signature is divisible by 16. If not, then, well, the same theorem tells you that this is independent of W. It just depends on y. So, for example, mu of the Poincare here is 1. Okay, so now let us go back to what we had here. So we have this element with values in theta 3H, and I actually want to get down to the Kirby-Ziebenmann invariant. And the way to do this is you look at this short exact sequence. 0 goes to kernel of mu, goes to theta 3H, goes to sigma 2, goes to 0 by mu. This will be an important sequence. And this induces a long exact sequence in cohomology. We have something in H upward 4 and delta CH, this C of K, clicks in here. And if we apply mu, basically if we apply a Rochlin to all the links, we get something in H upward 4 of M with Zima 2 coefficients. And this is exactly the Kirby-Zimmermann invariant. So, to review, well, notice C of K is 0 if K is PL. C of K was this element made out of the link, so if we have a piecewise linear structure, then all the links are spheres, which are 0 in homology cobordism. The image under the Rochlin is 0 if and only if, by the work of Kirby and Zimmermann, if and only if, well, the manifold has some other PL structure, not necessarily K. But, okay, so that's Kirby-Zimmermann. What we're interested in is not the existence of PL structures, but the existence of triangulations, of any triangulations. And what we observe is that if M is triangulable, well, then the Kirby-Zimmermann invariant is in the image of this map. So therefore, if we look at the connecting Bochstein homomorphism here to H5 of M kernel of mu, then this would be mapped to 0. Right? So this gets mapped to delta of M. There's some class in here, and this would be delta of M is 0. All right, so that's just an observation, but now one thing that Galuski's term and Matsumoto proved is that the converse is also true. So the manifold is triangulable if and only if, if and only if this obstruction vanishes in this cohomology.
So far, the Kirby-Zimmermann invariant is defined using a triangulation.
Yes, so I said that in general you can define it like this. And that's the
I see.
only definition that I know in general. But if it has a triangulation, you're just going to believe me that, yes, you can get it this way as well. Okay, so now we're interested in whether this obstruction can ever be non-zero. If there are non-triangulable manifolds, well, one possibility is that this Bochstein is 0, and that would happen if this short exact sequence split. So let's give it a name, star. So if we had some splitting, so some map like this, some section, so there's an observation, if star split, then the Bochstein for the long exact sequence would be 0. So then all manifolds would be triangulable, well, in dimension greater or equal than 5. All right, so the other result of Galuski's and Matsumoto is that, again, the converse is also true. Right, so what does this mean? It means that if star does not split, well, if star does not split, then there exists non-triangulable manifolds. dimensions in any dimension greater or equal than 5. And the way this works is as follows. So they construct some M5 with SQ1 of delta of M is non-zero. So the first inrod square. Right, so this is, well, they just give a construction. In fact, yeah, I think I will have time to give an example. But if you have this, so the first inrod square is kind of Bachstein for Z mod 4 going to Z mod 2. And, well, you just do some algebra, and you see that if you have a short exact sequence that does not split, like this, and the Bachstein for Z mod 4 is non-zero, then also the Bachstein for this mu is non-zero. So this is some, well, 5-minute algebra. This implies that delta of M is non-zero, assuming that this exact sequence does not split. And right, and then, well, like what I said here, then this is non-zero, so M is non-triangulable. So then you can take M, and you can also take products with tori. So M is 5-dimensional, but then you get examples in all dimensions. Here is an example of M5. Right, so non-triangulable. So basically with SQ1 of delta M is non-zero. So their example was different. This is a more modern post-Friedman example. I learned of it from Peter Kronheimer. So what you can do is you can look at a 4-manifold first, which is star of CP2 plus CP2 bar. So what is this? So this follows from Friedman's work that such a thing exists. It's some...
What does star outside mean?
Yes, it means that the intersection form is the same as CP2 plus CP2 bar, but the Kirby-Ziebenmann invariant is non-zero. So by the work of Friedman, such things exist for any, yes, this is non-smooth topological manifold.
Is it unique?
Yes, and it, also phi1 is not one. Phi1 is 1, simply connected, yes. So Friedman also showed that this uniquely determines X up to homeomorphism. And what you notice is that Q is the same as minus Q. So there is a automorphism on the intersection form. So that implies, again by Friedman, that there exists an orientation reversing homeomorphism F from X to X. And then what you do is just you take M to be the mapping torus of F. Okay, so exercise SQ1 of delta of M is non-zero. This is just because delta of X is non-zero and SQ1 is the cup with the Wu class, and because this is orientation reversing, it's kind of the thing that goes around the mapping torus. Okay, so this is going to be an example in dimension 5, and then you can take products with tori, and you can get them in other dimensions.
So M is non-oriented.
Yes, that's a good question. Yeah, so actually in dimension 5, all the examples are non-oriented. If you go to dimension 4, you can get orientable examples.
Are there examples with finite fundamental group in dimension
Yes, I think you can probably do surgery on them and kill some part of the fundamental group, but I'm not sure. Okay, so what we're left, so basically back in the 70s, it was already known that triangulability of manifolds in dimension greater or equal than 5 is equivalent to, well, to the fact that this sequence splits, and it turned out, but however, it turned out to be true that it doesn't split. So this is that exact sequence, the theorem that the exact sequence star does not split. So this is something about just this group, theta 3H, and the Rochlin homomorphism, and well, it's just about 3 manifolds, and this question came out of triangulation by looking at piecewise linear homology cobordisms, but in dimension 4 that's the same as smooth, so now we can just focus on smooth core manifolds. Great, so how do we prove this? So the idea is to lift mu to z. This is an old idea, I guess. Right. So we're going to construct a map beta from theta 3h to z. And the one I construct just happens to not be a homomorphism, but maybe there's some other map that's a homomorphism, I don't know. But it needs to have the following properties. 1, beta of minus y is minus beta of y. And 2, beta mod 2 gives us the Rochlin homomorphism. So if you have such a map, then what you can say is that if this sequence split, well, you could look at the image of 1 in here, and that would be some homology sphere y. So there would be some homology sphere y3 with, it's in the image of something from Z mod 2, so it better have the property that 2 times y is 0 in theta 3h, and then mu of y is 1. But 2 of y is 0 is the same as saying that y is equivalent to minus y. Right, and then we apply beta. Beta of y is beta of minus y. It's minus beta of y. That implies this beta is an integer. It implies that beta of y is 0. And then you reduce it mod 2, and you get that mu of y is 0. And that's a contradiction because we wanted mu of y to be 1. Okay, so then it remains to construct beta. Right, so, well, we want to say something about homology cobordism. So first let me say some, so the construction of beta was inspired basically by 2 predecessors. So first, I mean, kind of one attempt in this direction was the Casson invariant. The Casson invariant is something that associates to a homology sphere, some number lambda of y in Z, and it satisfies 1 and 2. So it's a lift to Z of the Rohlin invariant, but the problem with this is that it does not descend to theta 3h. So Casson defined this by, and this is what he used for the triangulation conjecture in dimension 4, but he defined it using representations to SU2. But it's not strong enough to detect things about homology cobordism. Right, so there are examples of homology spheres that are bound homology balls, but lambda equals 2. So mod 2, it becomes Rohlin, but not like that. The second one is the Froeshov invariant. So the Froeshov invariant is a homomorphism, and it descends to theta 3h. So it definitely satisfies 1 because it's a homomorphism, but delta mod 2 is not mu. So here you lose the connection to the Rohlin invariant, but you still gain something. You get, well, this is an epimorphism in fact. You get some structure on the homology cobordism, and the way Froeshov did this is, so this uses S1 equivariant Seiberg-Witten Floer homology. Right, so Floer homology, well, coming from gauge theory, is the typical example of a topological quantum field theory with some restrictions or and decorations by species structures, but it can tell you something about cobordisms. So if you have a cobordism, you get a map between the Floer homologies, and using that, you, well, I will explain in a minute how Froeshov did this. Right, so beta is going to be kind of it's like Froeshov, it's like delta, but using more symmetry.
So S equivariant comes because you go from 3 to 4 dimensions by throwing in a circle or something?
It comes from the constant gauge transformations. Let me explain. I'm getting to that in a moment. Yes. So let me start by explaining the Froeshov construction, and then I will get to beta. Okay, so let's start with some Seiberg-Witten theory for homology spheres. So first of all, we have to choose a metric to make sense of the equations, and then we write down some, there is some functional, the Chern-Simons-Dirac functional on, let me write, on the space of connections, which I can identify with imaginary one forms on Y, plus a space of spinors. In this case, since it's a homology sphere, there is a unique spin bundle, spin structure. And there is this map to R. I'm not going to write it down, but the important thing is that it's gauge invariant. So under the space of maps from Y to S1, and in fact you can kind of kill most of the gauge. So you can look at just the kernel of B star in here. This is the Coulomb slice. And if you do that, then basically you can look at this space, and this is and basically now you still have something. You have an action of S1, A phi. So if you have a connection, a form, and a spinor, it goes to A EI theta phi. So this is the S1, so there's a remainder, just the S1 constant gauge transformations. So now what you want to do.
Sorry, can I ask a question?
Yes.
I mean, is this just basically a billion Chern-Simons and then coupling the fermions with the...
Exactly, yes, that's right. So you want to do Morse theory, I mean you want to do Flirt theory for this functional. But the problem is that you have the S1 equivariance, and unlike in Flirt's original instanton theory, you cannot avoid the reducible. So there are the solutions. So basically, you want to define a group SWFC, kind of generated by solutions to Seiberg-Witten, meaning critical points of CSD. And the differential would count gradient flows from one critical point to another. Okay. Now, the issue is that the solutions are of two kinds. So there is one reducible, namely A equals phi equals 0, meaning that the action of S1 is trivial on this, and then there are some irreducibles, where the action is free. And you want to count them in some way. Well, you cannot put them on the same footing, so instead you can do an equivariant theory. Well, it's not so easy. There are various methods, so you can define SWFHS1 of Y. There are different constructions, so, well, Kronheimer and Rufka have a description for all three manifolds, but in this case for homology spheres, so I gave a construction a while ago, and then Freishoff has a different construction. Marcoli and Wang have a different construction. But in any case, all of them are supposed to give the same thing. And the way it works is that to the reducible, you would associate the equivariant homology of a point, and to each irreducible, you would associate the equivariant homology of a circle. Well, this is just Z. So I'm going to give an example. Here is a particular example. I'm going to take the Briskon sphere, sigma 2, 3, 11. But kind of the same thing happens in general. So here I'm associating the equivariant homology of a point, which is just CP infinity. So I get something like Z, 0, Z, 0, Z, so on. And to each of these I associate one Z. In general, you can have more things. Right, so this is the complex. There is a differential on this complex, and in this case there are two contributions. In general, you can have differential from irreducible to irreducible. And this depends on G. Depends on the metric. But then you take homology, and it doesn't depend on the metric, and this is, well, this is this. In this case, it's just Z, 0, Z, 0, Z, and so on. And then there is one Z here. Right, so this will cancel out. And further, you have additional structure. So this is a module over the equivariant cohomology of a point, which is the cohomology of CP infinity, which is Z of U. well, and in this case, right, so basically this decreases grading by 2. And so this is an example. In general, you always have one tower and then you have some finite part. Right, so now, well, this is cyber-written flavor homology. So there is some additional piece of information, namely the grading. And this is a connection to the Rochlin invariant. So you can put, it's the standard thing to do that makes it an invariant is to set this in degree NYG. So the bottom element is set in degree NYG. This is 2 times the index. Well, it's a combination of 8 time variants, but you can think of it as the index of the Dirac operator plus signature of W over 8, where W is a spin manifold with boundary YG, and then, well, you could add a cylinder. You could use Mathias-Bartholdi-Singer boundary conditions.
Is this manifold non-orientable now? No, this is orientable.
Now everything is orientable, right? So now we move to dimension 3, and all the links are homology spheres. Everything is orientable. Yes, everything is oriented. Right. So you can take a 4 manifold with boundary Y, and then look at the Dirac operator here, and this is kind of what is associated in the cyber-written theory to the reducible. And this is an even integer, and furthermore, this is even because this is a spin structure and the Dirac operator is quaternionic. So what happens is that this gives us exactly, well, if you remember the definition of the Rochlin invariant, this was just sigma mod 8, sigma divided by 8 mod 2. So this is 2 times mu of y mod 4. So, right, so there is this point. So this is the relation to the Rochlin invariant. But the problem with this is that it depends on the metric. So once you move here to an invariant of y, you can define the bottom degree in here. So this is 2 delta of y. This is the Furshov invariant. Is 1/2 times the minimal degree of infinite power in cyber-written flavor homology with S1 S1 equivariant. So this is an invariant, but now in this, for example, what happens is that this is 0 in this case, and mu is 0. So it's so once again, its reduction mod 4 is twice mu. If you go here, one irreducible interacted with the reducible, and somehow the bottom element moved up, and now delta is, well, this is in degree 2. So it's class mod 4. If I divide by 2, I end up with 1, and that's not 0 mod 2. So that's not mu mod 2. And this is the failure of the Furshov invariant to give us back the Rochlin invariant. It stems from the fact that there is interaction between the irreducibles and the reducibles. Okay, but the interesting thing is that it still gives you a map to theta 3h. So the way to prove that is to consider the cobordism. So you have a homology cobordism from one manifold to the other, and this induces a map from flavor homology to flavor homology by a TQFT, and you can show that it's the identity. I mean, you can show that it's non-trivial on the towers, and from that it follows that the bottom elements are the same. So from some algebra. So delta descends to theta T. Okay, so I have 5 minutes for the, actually, when did I start? Did I start on time?
Oh, we started at 5 past. No?
Okay,
So
then
you
I
have
have
10
one.
minutes.
Okay, great. So, right, so now we want to fix that. And beta is like delta, but with more symmetry. Did I keep? Okay. All right, I think I can. Okay, so let me just remind you what we want. We want theta from theta 3h to z. Beta of minus y is minus beta of y, and beta mod 2 is mu. Okay, so what we're going to do is we're going to use the pin 2 symmetry. Of the Ciprian equations. So, right, so in this case we're on a homology sphere, we have a spin structure, and yes, there is this additional conjugation symmetry. So first of all, let me say what pin 2 is. Pin 2 is S1 union JS1. It's two circles inside C plus JC, which are the quaternions. So it's a non-abelian group made of two circles.
They intersect one point or what?
No, they're just
I said, unit circle.
1 j, 1 minus j minus 1. So j squared is minus 1. Yes, j I is minus 100. Right, so we already know that S1 acts on our space, on the Coulomb slice by gauge transformation. And then we have, right, so CSD is invariant under P2. So S1 we already know how it acts, and there's this additional symmetry J, and this takes A phi to minus A and phi J. So phi is a spinor, it lives in some quaternionic vector bundle, and we can apply J to it, and then A gets taken to minus A. So this is the conjugation symmetry on spin C structures. In this case, there's a spin structure and it's preserved under conjugation. Right, so then, again, there's some story that I'm skipping, but you can define a pin 2 equivariant Cyber-Witten homology. It's more difficult to define it. There are two constructions. So the way I did it was by finite dimensional approximation. And then Francesco Lin gave a more theoretic, Morse-Bott Floer theory version of it, based on the Kronheimer-Brovka definition of Cyber-Witten Floer homology. In any case, whatever it is, it's going to be a module over the cohomology of B pin 2. And let me use Z mod 2 coefficients. So I'm going to introduce the field F, J over F to the field with two elements. And this you can compute. It's F of Q and V mod Q cubed. Where, well, degree of Q is 1 and degree of V is 4. So the way this, I mean, basically B pin 2 is an RP2 bundle over HP infinity, over the quaternionic projective space, and you get some V in degree 4 from HP infinity, and you get a Q in degree 1 from RP2, and Q cubed is 0. So, let's see what the complex would look like. So for sigma 2, 3, 11, we still have this. But now these are related by J. And this is the situation in general, so you're going to have one reducible, and then the P interaction is free outside, so everything gets paired up. And now, to this, we associate the homology of BP2, and to each such pair, we associate the P2 equivariant homology of P2, which is just the homology of a point, which is F with our Z-macro coefficients. So what we get is something like F, 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 0, F, 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 0, and so on. And here we get a single F. And here we had basically two flow lines, and they kind of become one. So there's one differential like this. So let me maybe move it up. So this is a general situation. What you have is this tower. I mean, you still have these towers, but now instead of the action of U, you have an action of V. Which has degree 4. And then you also have the action of Q. But actually, we're not going to care about that. We care about the thing coming from the quaternionic projective space, which is infinity. So, right, and this still lives in degree n yg, which is congruent to 2 mu mod 4. Alright, so now we take homology. In this case, these things cancel. We're left with F, F, 0, F, 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 and so on. What happens in general is that you have this tower and again some finite part. So if you look at the action of V, you end up with 3 towers. So there's 3 towers ending in degrees A, B, and C, where A is congruent to 2 mu mod 4, B is congruent to 2 mu plus 1 mod 4, and C is congruent to 2 mu plus 2 mod 4. So the important thing here is that now we have a 4 periodicity instead of a 2 periodicity. And that allows us to keep the connection to the Rochlin invariant. Because, right, so this one lives in this degree. And then there's some interaction with the irreducibles, some differential. In fact, there can be some other V map. But in this case, this got killed. But the next thing is the same mod 4. It's in the same degree mod 4. So in this case, A is here. A is 4. This was 0 here. The original degree. Then we have the next V thing lives here in degree 1. And then C lives in degree 2. These are the bottom elements. But we have this congruence as mod 4. So we can say what they are mod 4. Right. Okay, so now we can just, well, let's renormalize. Let alpha be A over 2, beta be B minus 1 over 2, and gamma be C minus 2 over 2. And these are all now lifts of the Rochlin invariant. So these are all mu mod 2. And furthermore, they descend to maps from theta 3h to z. So this is just like the Freud-Shove story. So here we had the bottom element in S1 equivariant homology, and we used the TQFT property, and right, we could prove that it descends to a map. Similarly, all 3 of these descend to the maps to theta 3h. And then the final thing, okay, so then we want to just check this. So you have to study what happens under orientation reversal, and what happens is that you use some equivariant Spaniard-Whitehead duality, and kind of the tower gets reversed. So, right, so you take, well, what happens is basically that the first tower and the third tower get switched. So you get that alpha of minus y is minus gamma of y. But the middle tower remains fixed, and you get that beta of minus y is minus beta of y. Okay, and this is what we wanted. So we construct a beta that descends to theta 3h because of TQFT properties of Ciprian, satisfies this and lifts the Rochlin invariant. And then this shows that the Manolescu-Stern-Matsumoto sequence does not split. All right, so I'll stop here.
Are there any questions?
Why don't you write down alpha and gamma? You don't use them.
Yeah, I don't use them, but just
Yeah, okay.
yes, to see that they exist as well. I mean, you get more information about theta 3h. Now we can try to see which manifolds are homology covariant to each other. Yes.
So did you say all of the non-triangulable manifolds in dimensions higher than 4 are non-orientable?
No, just in dimension 5.
Or just in dimension?
Yes, so this was proved by Ciprian before Galuski, Stern, and Matsumoto, but yeah, so we had that non-orientable example in dimension 5. What you can do is you can take the non-oriented bundle over it, the double cover, and there's an S1 bundle associated with that. And that is now an oriented manifold, and it's 6-dimensional and it's non-triangulable.
So how does one construct non-triangular manifolds in the dimensions? They don't take one of these 5-dimensional ones. The cross with some.
With the torus.
A torus
That's
is fine.
That's
So
fine, yes. Yeah, minus
Okay.
5.
I
Yes.
knew you will answer finite type.
That's a good question.
Because
Probably not.
Casson is, right?
Yes,
Casson
yes,
is.
Casson is, there is, I mean, one needs to understand how they behave under surgery, and they do behave in some way. So Francesco Lin has a paper where he establishes an exact triangle for surgeries on, for the Cyber-Gooden fluid homology, but I mean, it's kind of complicated, so I don't think they satisfy the same kind of relations. that
Or
finite
most probably not, but you invariants are more numerical.
Even numerical, I mean, I don't know, but my guess is not.
Okay. Thank you very much.